So last time we talked about uh, some sort of tail inequalities, which we said we can kind of use to rule out the probabilities of, or sort of bound the probabilities of uh, what we might call bad events, or rather uh, show that the probability of a certain desirable event is fairly large. And we said the way of using these inequalities to try and set up random variables in such a way that that the tail of the random variable, or the probability that it's kind of larger than a certain quantity, captures the event we want to avoid. And so and then we'll see applications of how to try and set up a random variable in this fashion. And we developed these two inequalities: Markov's inequality, which is only in terms of the expectation of the random variable, which is usually it's possible to compute. And then basically just applying Markov's inequality on a slightly different random variable, we obtained Chebyshev's inequality, which for a random variable z is in terms of its variance. And we saw that in certain cases, when you can compute the variance, you can obtain stronger bounds on tail probabilities. Although you need more information to do this. In particular, you need to be able to compute variance. And depending on how complicated your random variable is, and maybe how energetic you are feeling at the moment, it may or may not always be possible to compute the variance. So it's just that, yeah, depending on how much information you have about the random variable, you can obtain inequalities of varying strength. Okay. And I kind of started talking about this application, which was about what I call threshold phenomena. So in particular, we wanted to analyze the event whether or not a random graph contains a copy of H. And so here, the probability space corresponded to outcome, or the choice for G. And we said G was drawn from this distribution, G and P, where each edge, or sort of each pair ij is, these are rather unordered pairs. I can write I comma G. So each pair is chosen to be an edge with probability P, and it's not an edge, or the edge is not present with probability 1 minus P. And we wanted to analyze when does a graph drawn at random from a distribution of this form contain a copy of another graph. In particular, we were talking about this graph H, which is the graph on 4 vertices with all 6 edges present, and this is called a 4-clique. And in general, a k-clique is a graph on k vertices with all k choose 2 edges present, and this is just the case with k equals 4. Okay. Any questions about any of this before we proceed to analyze it? Okay, and we claimed something of this form, that there is a certain sort of threshold value for P, and when P is asymptotically less than n to the minus 2/3, or rather the limit of P divided by n to the minus 2/3 goes to 0, then the probability that G contains a copy of K4 goes to 0 as n goes to infinity. And the reason this expression depends on P is that the probability is over G sampled from this distribution G and P. And similarly, when we claim that when the parameter p is asymptotically greater than n to the minus 2/3, or the limit of p divided by n to the minus 2/3 goes to infinity, then the probability that a random graph G drawn from this distribution contains a copy of K4 goes to 1. Okay. And we claimed this, we didn't quite prove it, but we gave one natural sort of argument for why something interesting happens at n to the minus 2/3, which is that the expectation of Z, or the expectation of the number of copies of K4, either goes to 0 or infinity, depending on which side of n to the minus 2/3 P lies on. Okay. Any questions about this? Okay. And let me just also remind you of how we were computing this expectation. The number of copies of K4 can be written as a sum of indicator random variables. We defined a copy as some subset. Was there a question? Sorry. Okay. We defined a copy of K4 as some subset of 4 vertices which has all 6 edges present. So we're going to just sum over all subsets of size 4 of the vertex set, and where the vertex set is of size n. And the sum will be over all indicators, whether this particular subset C of size 4 has all 6 edges present or not. Okay. And now we'd like to use our knowledge of this and Markov's and Chebyshev's inequalities to maybe prove the kind of bounds on probability we were talking about. Can someone say something? It's just really quiet, and I'm not sure if my sound is working correctly.
Yep, your sound sounds good.
Okay, thanks. All right. So let's first look at the regime when p is small. In particular, it's asymptotically smaller than n to the minus 2/3. And recall what we want to prove here is that the probability that the graph G contains any copy of K4, and Z is the number of copies of K4. So the probability that the graph G contains any copy is the same as the probability that Z is greater than 0. Z is just counting the number of copies. And we want to show that this probability goes to 0 in this regime when little p is quite small. This is smaller than in particular n to the minus 2/3 asymptotically. Okay. And recall that Z is the number of copies of K4. So in particular, Z is a random variable which takes only integer values. It's the number of copies, so it's either 0 or 1 or 2 and so on. So it's a non-negative random variable, and it's an integer valued random variable. So we can say that Z is greater than 0 if and only if Z is greater than equal to 1. Because the only value which is allowed after 0 is 1, nothing in between. And this threshold is large enough to actually apply Markov's inequality. So Markov's inequality tells us the probability of Z greater than equal to T is expectation of Z divided by T, where T is just 1. And we already computed the expectation of Z on the previous page, which is n choose 4 times p to the 6, just using linearity of expectation. So, and we already know that this goes to 0 as n goes to infinity when p is asymptotically smaller than n to the minus 2/3. We know that the expectation goes to 0. So the probability of Z being greater than 0 also goes to 0. In particular, it's upper bounded by the expectation, which proves half of the result we claimed. And we'll get to the rest, sort of the other half in a moment, but any questions about this?
Could we maybe really quickly go over the expectation of Z again?
Yeah, of course. Right, so recall that we wrote Z as summation of x sub c, where C is a subset of, let's say, the vertex set 1 to n. Size of C is 4. X sub C is an indicator, which is 1 if all 6 edges between vertices in C and 0 otherwise. Okay, and stop me if any of these definitions are unclear, if any expression I'm writing here doesn't make sense. So by linearity of expectation, we know that what we need to compute is just expectation of x sub c. And x sub c is a binomial, or sorry, is a Bernoulli random variable. So expectation of x sub c is just the same as the probability that x sub c is equal to 1. This is always true when we have a random variable which takes only values 0 or 1. And now we want to just analyze what is the probability that x sub c is equal to 1. So C is a set of 4 vertices. And x sub c is 1 if and only if all 6 pairs of vertices are connected, or all 6 edges are present. Each edge is present with probability p independently. Because we said we define a graph G and P in such a way that every edge is included independently with probability p. So the probability that x sub c is equal to 1 is equal to p to the 6. And the number of choices for C is the number of choices for subsets of n of size 4, which is n choose 4. So we get n choose 4 times p to the 6. Is that okay?
Yeah, thank you. I was mostly concerned about the n choose 4, but that makes sense. Thank you.
Okay. Right. So now let's go to the second half of what we claimed, which is that when p is asymptotically larger than n to the minus 2/3, then, okay, so let me write down what we want to claim here. We want to say that the probability that G contains a copy of K4, or Z is greater than 0, tends to 1. Now, the tail inequalities we have so far don't really tell us how to say that some probability is large. They tell us how to show that some probability is small. So what we will actually show is that the probability of z being 0 is very small. And z is, again, a random variable which is integer valued, and in fact, it's non-negative. So if we show that it's not 0, or the probability of being 0 is very small, then the remaining probability, it has to be greater than 0. In particular, at least 1. So we'll actually try to understand the probability that z is equal to 0. And the probability that z is equal to 0, why do we actually even expect it to be small? Well, we know that in this range of parameters, the expectation of z is large. And so if the expectation of z is fairly large, for z to be 0, it will have to be very far from its expectation. And we know this doesn't happen if we can understand, or if we can understand how large the variance is, and in particular, if we can say that the variance is not too large, then we don't expect z to be very far from its expected value. And one way of formalizing it is to say that, well, how far will z will have to be from its expectation? Well, by an amount which is equal to its expectation for it to be 0. Expectation is some positive number, and it has to be at least that distance. Well, exactly that distance. And we know by Chebyshev's inequality that this quantity can be upper bounded by the variance divided by the amount of deviation whole squared. So it comes down to understanding the variance. We already understand the expectation, so the denominator we know how to write down. It's the numerator that we need to understand. And as opposed to, so, okay, let's write down what z is and how do we kind of write each of these terms. So recall that z is equal to summation x sub c. Previously, when we wrote things this way for a binomial random variable, we could use the fact that the terms occurring in the summation were independent, and so the variance of z was just the sum of the variances of each of those terms, or we could come up with a relatively simple expression for the variance of z. And we said this is also true whenever you have a sum of pairwise independent random variables. In fact, we kind of half proved it. This is not necessarily true for all the x sub c's or the random variables that appear in the summation here. So the amount of dependence between, let's say, if you have C and D, which are subsets of the vertices, then the amount of dependence may kind of vary. So for example, if you have C and D, which are disjoint set of vertices, then the edges which kind of determine the random variable x sub c are just completely disjoint, and it makes sense that there won't be too much dependence. But there may also be sets C and D which are kind of highly overlapping. Well, with the special case that C is equal to D, but even more generally, you can think of C and D which are highly overlapping. So for example, this set and this set. And then it may be the case that there is some dependence between C and D. The way we will capture this, and I'll kind of do a slightly longer calculation for the variance, is by defining what I'll call the covariance of the random variable x sub c and x sub d. And then we will see how to understand variance. This so this is very similar to a computation we did earlier, but we will expand and take more care with a few terms. So expectation of z squared, z can be written as summation x sub c. And expectation of z whole squared can be written as expectation of we can open up the summation of x sub c as having two indices x sub c and x sub d, all inside the expectation. And here we'll have a very similar looking expression, but it will be a product of expectations rather than an expectation of a product. And then we can use linearity of expectation to let it for individuals of each C and D. And this is a quantity I will call the covariance of x sub c and x sub d. And we will use this to measure how dependent are C and D on each other, or sort of how far are we from the example of pairwise independent random variables or mutually independent random variables that we analyzed earlier. Okay. Just a quick sanity check. Let me just analyze this quantity in two special cases. So what happens when C is equal to D? And what happens when x sub C and x sub D are independent? Okay. Can anyone tell me just what happens to the covariance when x sub C and x sub D are independent? Kyle, if you're trying to say something, you're muted. So, yeah.
No, I thought I had something and then I didn't have anything.
Okay.
Would the covariance be 0?
Yeah. So when they're independent, we know that for two independent random variables x and y, expectation of x times y is equal to expectation of x times expectation of y. And that's exactly what we have here. Expectation is, so if x sub c and x sub d are independent random variables, then expectation of the product will be equal to the product of expectations. And so the covariance will be 0. Okay, what about the case when C is equal to D?
Is that also 0? Also 0?
So also 0. Okay, so one notice that then we don't have independence because, well, X sub C, X sub D, which is again X sub C, are not independent. They are actually the same thing. So random variable is not independent of itself. But we can write it in a different way. So X sub C times X sub D is just X sub C whole square. And the second term can be written as expectation of X sub C whole square. Now, what do we know about this?
That looks like the variance.
Exactly. So this is just a variance of X sub C. So in particular, for whatever reason, okay. The concept of covariance is just a generalization of variance. So variance is when we are analyzing a single random variable, and the covariance can be sort of generalizing it to the case of two random variables. And it sort of interpolates between analyzing two independent random variables versus analyzing a single random variable or two copies of the same random variable, in which case they're of course dependent, and it sort of captures things which may be in between. And we'll see that we will be able to quantify how far things are from being independent using this concept. But there's one way of quantifying it, by the way. This is by no means a unique way of quantifying this kind of dependence or independence, but it's one way which is often quite useful. Okay.
Really quickly, is anyone else the sound off? Or not off, but just like distorted?
A little bit for me, yeah, but it fixed itself a second ago.
Yes, same
Okay.
here.
Okay.
Okay, yeah. So there might be an issue with your sound.
I see. It might be an issue with my internet connection. Let's see. Is it still off?
It sounds a bit distorted for me still, but it's not like lecture breaking.
Okay. Let me try to continue with the hope that, and it was okay in the beginning of the lecture, right?
Yeah, it was.
Okay. Let me try to continue with the hope that it'll be okay in a couple of minutes, but if not, please stop me.
Awesome. Thank you.
Okay. So now I claim that we can actually compute the covariance of X sub C and X sub D, or so recall that we said, or what we just said was that the variance of Z is the sum of the covariances. So if for all pairs C and D, we can compute the covariance, then we can compute the variance of Z. Okay. It's a little more complicated than applying linearity of expectation or sort of just analyzing each X sub C by itself, but now we have to analyze two of them, which seems reasonable because variance is kind of a square quantity. Okay. And I claim all we need to know is to compute this covariance is what is the size of the intersection of C and D. C and D are, remember, subsets of vertices of size 4 each, and their intersection sizes might be different. So let's start with intersection 0 and kind of work our way upwards. What does it mean that they are subsets of vertices with intersection size 0? Well, that they are just disjoint subsets of vertices. And X sub C is 1 if and only if these 6 pairs of vertices are all present in as edges. And X sub D is equal to 1 if these other 6 pairs of vertices are all present as edges. Any guesses or answers on what the covariance should be?
This is that first case we were talking about where it should be 0, right?
Right. So because X sub C and X sub D depend on disjoint sets of or disjoint sets of edges, or sort of the 6 pairs which determine whether X sub C is 0 or 1 are disjoint from the 6 pairs which determine whether X sub D is 0 or 1. And for independent events, we know the covariance is 0. So the covariance here is just 0. Let's look at case 2, where the intersection size is 1. So let's draw a representative picture. So they overlap in one vertex. So let's say we draw it like this. Okay, what about now? I could guess.
Is it maybe 1/4?
1/4. Why is that?
Because 1/4 of the vertices of each square is contained in the other square.
Okay. So first notice that 1/4 may be too high an estimate anyway, because we are computing the covariance, and we define the covariance as expectation of X sub C, X sub D minus expectation of X sub C times expectation of X sub D. Right? And these quantities may be small. In particular, the expectation of X sub C, X sub D is equal to the probability that x sub c is equal to 1 and x sub d is equal to 1, right? Because the product is a 0, 1 variable also, and the product is 1 if and only if both x sub c and x sub d are 1. And the probability that both are equal to 1 is the probability that all 12 pairs are present as edges. So it's p to the 12. So the maximum the covariance can ever be is p to the 12. And in particular, if p is very small, which is the probability of an edge, if it's very small, then 1/4 might be too high. Even if p is, let's say, 1/2, which means that we are, for every pair, we sort of toss a fair coin and either include an edge or not. The probability that, or sort of the covariance can at most be 2 to the minus 12. So 1/4 might be too high a bound anyway. Does that make sense?
Yeah. I see that now. It's way too high.
Right. So, but I mean, another thing that, so there are kind of two ways to compute the covariance in this case. We're kind of halfway done with the computation, so maybe we can finish that one. Can anyone tell me what the expectation of x sub c is? We already computed this, but I'm just asking you to remind me.
N choose 4 times p to the 6.
Not the n choose 4. This is just one of the indicators.
Oh, so just p to the 6.
Same for this. So what's this expression? It's just 0. Actually, we can say this is 0 for exactly the same reason we said the covariance was 0 in the previous case. We said x sub c, whether it's 1 or 0, is determined by these 6 edges, the 6 red edges. And whether x sub d is 0 or 1 is determined by these 6 edges. And different edges are independent. So in particular, this set of six edges is independent from this set of 6 edges. And so x sub c and x sub d are independent random variables, which implies the covariance is 0. Everything I said there is still true here. X sub c is determined by these 6 edges, or these 6 pairs of vertices, which the set of pairs is disjoint from these 6 pairs. And so x sub c and x sub d are still independent random variables, and their covariance is 0. The fact that they overlap, that c and d overlap in one vertex, still means that they don't overlap in any pair. And x sub c and x sub d are determined by whether a pair is present in an edge or not. Does that make sense? So, I mean, we can of course compute it directly, but I'm also trying to emphasize that they are still independent, and because they don't overlap in any pair of vertices, then the randomness is in the choice of whether a pair is included as an edge or not. For the rest of them, we will have to do this computation, but fortunately, we saw how to do the computation explicitly in the previous part, so we can keep going. When they overlap in two vertices, sort of a representative picture looks like this. So one pair is common between the two, and You're still trying to compute the covariance, which can be written as the expectation of x sub c, x sub d, minus expectation of x sub c. This quantity is always the same. It's just the product of p to the 6 times p to the 6. So it's always p to the 12. It's the first quantity which is more interesting. Okay. And now, as before, it's still the probability that x sub c is equal to 1 and x sub d is equal to 1. But now, these are no longer independent events. In particular, there are 11 pairs of vertices, because one pair is kind of common to C and D. If all of them are present, then x sub c and x sub d are both 1. So this probability is p to the 11 rather than p to the 12. Okay. Any questions about that? Feel free to stop me. Similarly, the case when they overlap in three vertices is similar. So when they overlap in three vertices, is p to the, and the probability that x sub c is 1 and x sub d is 1 is equal to p to the 9, because there are 9 distinct pairs which all have to be present as edges, so that all 4 vertices in C are connected, which means all 6 edges there are present, and all 4 vertices in D are connected, because when they share 3 of their vertices, the set C and D, they share 3 pairs of vertices which need to be present as edges. The second part is still p to the 12. So the covariance is p to the 9 minus p to the 12. And finally, for the last part, then C intersection D is equal to 4. C has to be equal to D. And so x sub C is equal to x sub D. And we are computing the variance. And this we know already how to compute. It's the probability of the expectation of x sub C whole square minus this. The first term is p to the 6, just because x sub C is 0 or 1, so x sub C whole square is equal to x sub C. And this is p to the 12. Okay. So there's a little bit of a case analysis, but it's an illustration of how we can try to understand the variance even when we don't have pairwise independence or some relatively simple kind of structure. In some sense, when we were analyzing pairwise independent random variables, we were always either in the sort of complete independence case, so we were always either in a case like this, or in a case where we had exact equality and the stuff in between did not happen. So in particular, the combinations we did here should also prove that for the sum of pairwise independent random variables, the variance of the sum is equal to sum of variances. But this gives a generalization.
Really quickly, what in particular does a negative, like either variance or covariance mean? Because all of these values, except for case one, are going to be negative.
No, they are not negative. So p to the 12 is smaller than p to the 6. P is a probability, it's between 0 and 1. So all these values are actually positive. But a covariance can be negative.
Oh, sorry, yes. Okay, yeah, sorry, continue.
No, okay. But yeah, we can discuss later after the lecture. So in particular, when I was saying that the covariance measures some notion of how dependent two things are, this is mostly about the magnitude of the covariance. The sign itself can be negative. It won't be negative when C is equal to D when we are looking at the variance, which is a non-negative quantity always, but not. But otherwise, we don't give any guarantees in general. So in particular, if you think of a Bernoulli random variable, two random variables which are just complements of each other, then you can check that the covariance will be negative. And we can talk more about the lecture, more after the lecture, and sort of how we may want to interpret them. In some sense, it's what we usually say as things are negatively correlated, that one of them is increasing, then the other decreases, and so on. And this is the sign of the covariance being negative captures some notion like that.
Awesome, thank you.
Okay. Okay, so now kind of did all the computation we needed to do, and this is just putting things together. We already know the variance is equal to the sum of the covariances, and I did a little bit of counting here. This is the case when C is equal to D. This is the case when C intersection D is equal to 2. And this is the case when C intersection D is equal to 3. Because when the intersection is 3, we are basically choosing 5 vertices. And out of these 5, we could choose any 4 to form our C. And the remaining 1 vertex will correspond to the new vertex in D. And some similar computation for when we are choosing 6 vertices with an overlap of size 2. I mean, the exponents of n and p which really matter. The rest I'm just hiding or suppressing as constants using this order notation. So once you write things that way, maybe one more step of computation to understand this ratio, which is said by Chebyshev's inequality, is an upper bound on the probability of z being 0. Can't quite use order notation yet for the denominator because I don't want an upper bound on the denominator. I need a lower bound, but I can compute the denominator exactly. And then we can write it in order notation just by sort of canceling the right kind of terms. And I'll leave it to you to check that each of these terms goes to 0 as n goes to infinity, provided that p is asymptotically larger than n to the minus 2/3. So in particular, for the first term, you can see this denominator goes to infinity, which means that the ratio goes to 0. And similarly, you can check for the other terms. So we get that the probability that z is equal to 0 goes to 0, which implies that the probability that z is greater than or equal to 1 goes to 1 in the regime when p is asymptotically greater than n to the minus 2/3. Okay, so mostly, I mean, this sort of threshold phenomenon is kind of a bit of a surprising phenomenon when you see it for the first time, that the probability as a function of this parameter little p either tends to 0 or tends to 1. So there is no choice of, okay, there is some kind of ambiguity when p is maybe somewhere around n to the minus 2/3, but other than that, you have a fairly sort of strong dichotomy that either a random graph contains a clique of size 4 with overwhelmingly large probability, or it just doesn't. And this sort of thing happens in a lot of random models for a lot of properties, not just containing K4, not just containing copy of another small graph H, but in much more generality. I'll say more in the notes with some references to kind of more general results of this flavor. But I also like it for just this analysis, which shows that even though you don't always have independence between x sub c and x sub d, you can say that there are some cases in which they have independence, and most pairs C of C and D are of this form. So if you go to the counting on the next slide, then we can actually count how many pairs C and D are of the type where we don't have independence, and you can say that you can check that these are a minuscule fraction of the total number of pairs of subsets C and D that we can get. So there is some independence, there is some dependence, but it's kind of limited. Then even in those cases, we can quantify how much dependence is there. This is a slightly more refined version of analyzing sums of pairwise independent random variables. Okay. Any questions about this before we proceed to the next topic? Okay, so now let us return to the sums of independent random variables. But this time, use much more about this independence than what we would by just computing variance. So let's say Z is a sum of x1 to xn, where x1 to xn are mutually independent Bernoulli random variables. To add a little more generality to our result, let's say that they are not identical. Xi is a Bernoulli random variable with parameter pi, which means that the probability xi is equal to 1. Is equal to pi. And probability 1 minus pi, it's 0. Just a quick sanity check. What is the expectation of Z?
The sum of 1 to n of pi.
Right. So yes, by linearity, it's expectation of of expectation of pi, because it's a Bernoulli random variable, expectation is just the probability that it's 1. Okay. So to state our bounds, let's call this mu. And state our bounds in terms of mu. So we will be still interested in bounds of the form, when does z deviate significantly from mu? When is it much larger than mu, or when is it much smaller than mu? The kind of things we were studying in Chebyshev's inequality. But since we will be able to obtain much sharper bounds using the fact that x1 to xn are mutually independent, then I call that in Chebyshev's inequality, we just computed variance. For variance, it didn't really matter whether things were pairwise independent or mutually independent. In both cases, we just got that the variance of z was the sum of the variances of each of the xi's. So we didn't really use mutual independence in the fullest possible way when we were applying Chebyshev's inequality. And here we'll see that if we can use mutual independence in a much stronger way and obtain much sharper bounds. Okay. So the bound we will prove, or one of the bounds we will prove, is of the form on what is the probability that z is, let's say, 1.5 times its expectation, or 1 plus delta times its expectation. And ignore the bound on the right hand side. It's some expression we will get by kind of optimizing sort of some parameters. But what I do want you to remember is the method of proof here. It's the same idea which is useful in many different situations. It's a common way of exploiting mutual independence when you're trying to prove concentration inequalities or tail bounds. And I mean, the simplified version, which I'll come back to, is sometimes applied directly, but the method of proof is applicable in many more situations. We'll also see it comes up in kind of analysis of dimension reduction. It also is very useful when you're analyzing random matrices and so on. So I want to emphasize the method much more than the exact bound. But bound is also very useful, but the method is even more so. Okay, so to analyze the probability that z is greater than or equal to 1 plus delta times mu, as in the case of Chebyshev, we will basically apply Markov's inequality to maybe a slightly different random variable. In case of Chebyshev, we applied it to z minus mu whole squared, which we called y, and we applied Markov's inequality to this new random variable. We'll do something very similar, except that the new random variable we'll define will be exponential in z. So let's call this y. And we define y to be e to the lambda z. And lambda greater than 0 is a parameter which we'll choose later. So the reason this is equal is that for all lambda greater than 0, e to the lambda x is an increasing function of x. And in fact, it's a strictly increasing function. So e to the lambda z is greater than or equal to e to the lambda times whatever was on the right hand side of the previous inequality, if and only if z is greater than or equal to 1 plus delta times v. And this is true for any lambda which is greater than 0. So let me just write this for some value of lambda to be chosen later, and then we'll kind of try to optimize lambda in such a way that it gives us the best possible bound on the probability. But no matter what lambda we're planning to choose for any lambda, we can apply Markov's inequality. So we can upper bound this by the expectation of y or expectation of e to the lambda z divided by whatever appears on the right hand side. And notice that we are applying Markov's inequality because y is a non-negative random variable. Any questions about this step? Okay. So in some sense, it's kind of continuing what we were saying earlier. If you can compute the expectation of z, you get some bound. And then I said, if you can compute the variance of z, you get a potentially stronger bound. And now we are computing some even funkier looking quantity, which is the expectation of e to the lambda z, which is this kind of called the moment generating function of z, or it's an exponential moment and so on. So if you can compute some quantity like this, which may be potentially even more difficult to compute than the variance, but if you can, you get a really strong bound, and then we'll see what those bound looks like, what that bound looks like, and how to compute it when z is a sum of independent random variables. So using the fact that z is a sum of independent random variables, we can indeed compute it. So let's start. So we want to calculate expectation of e to the lambda z. We can write it as and start with the fact that z is a sum of independent random variables, a sum of the xi's, and the xi's are also mutually independent. The way we will use that is, and the reason we actually did this exponential trick, also called the Laplace transform, is that an exponential of the sum, or sort of, is a product of exponentials. So here we get e to the lambda times xi. And now we use the fact that xi's are independent random variables. And okay, maybe it takes a little bit of thought to convince ourselves that this means that variables e to the lambda xi's are also independent. So e to the lambda x1, e to the lambda x2, and so on are also random variables. And I claim that if the xi's are mutually independent, then so are this new collection of random variables are also mutually independent. And then we can write it as a product of expectations. So this is where we really used independence. And this is something, again, we've been doing for sums of random variables, that we reduce the task of computing a sum or an expectation of a sum to a sum of very simple expectations. Here, using mutual independence, we actually reduce the task of computing an expectation of a product to a product of what will turn out to be relatively simple expectations. So now we're down to computing an expectation of e to the lambda xi. And this I claim is actually not too bad, because xi is a Bernoulli random variable. So it only takes two values, 0 or 1. And so the probability pi xi is 1. And we get e to the lambda xi is just e to the lambda. And the probability 1 minus pi xi is 0. And so e to the lambda times xi is just 1. Okay. So we can compute this number exactly. It's we will need to massage it a little bit so that we can derive some sort of clean bound out of it. But that is just a couple of kind of analytic tricks. But this, as far as computing this number is concerned, we can actually find it exactly. Now let's sort of rewrite it in a slightly more convenient way so that we can calculate this product and obtain some nice bounds. So maybe this is just rearrangement, writing in terms of coefficients of pi. And the next the arrangement is just motivated by the fact that what we really want to compute is the product of these guys. So the expression we wanted to compute, we know exactly. It's a product of terms of the form 1 plus pi times e to the lambda minus 1, but it's not such a convenient expression to work with. In particular, we wanted bounds in terms of mu, which was a summation of the pi's. And this expression, when we open it up, we'll get all kinds of products of pi's and so on. So although we know it exactly, it will be a fairly messy expression to work with. A relatively kind of standard way to go from this kind of a product to, again, a sum of the pi's in the exponent is to use the inequality that 1 plus x is less than equal to e to the x. This is true for all x. Excuse me. And yeah, you can try to check the proof by just maybe checking the value and saying that equality holds at x equals 0, and then check the derivative on both sides. But using this inequality will give us a nicer way of understanding the expression we want. So let's continue. And let me just. So we wanted to calculate product of this, and we said its product of I is equal to 1 to n 1 plus pi times e to the lambda minus 1. And then using the fact that calling this quantity x and using the fact that 1 plus x is less than equal to e to the x, we get a quantity where p to the I is in the exponent, but this 1 in front is gone. And then we can use this product to again get a summation. So then pi is again sum up in the exponent, and we just get e to the lambda minus 1 is just some constant, but depends on the parameter lambda. And the summation of pi's is nice. It's e to the mu times this stuff. So what is the bound we get? Recall that we said probability of z being greater than equal mu was less than equal to, using Markov's inequality, this expression divided by e to the lambda times 1 plus delta times mu. And we just proved an upper bound, which is e to the mu times and divided by lambda times 1 plus delta times. So, and actually we proved this bound for all lambda greater than 0, because we said for every lambda greater than 0, we can look at e to the lambda times z, which is a strictly increasing function. And so the application of Markov's inequality holds no matter which lambda greater than 0 we choose. So it simultaneously holds for all lambda. And then we will use, we want to choose lambda, which minimizes the bound. Or given us the tightest possible bound on the probability on the right hand side. And to do this, I mean, basically set the derivative to 0 and check what value of lambda you get. Quick computation. I mean, you can write it as e to the, let's see, u is common, and you get e to the lambda minus 1 minus lambda times 1 plus delta. So to find the best lambda, let's set the derivative of which gives or lambda as plugging this value of lambda in the bound, you can derive this expression that we had, just substituting lambda as ln of 1 plus delta, or e to the lambda as 1 plus delta. So in some sense, we did a generic transformation which holds for all lambda, and then just computed whichever lambda gives us the best possible bound with that. Okay. Any questions about this? As an exercise, check that you can also prove a bound when z is on the probability that z is significantly smaller than its expectation. And just because Markov's inequality kind of gives us bounds on when something is large, one way to apply this is to just say that this is equal to the probability that e to the minus lambda z is greater than equal to e to the minus lambda times 1 minus delta times mu for positive lambda. And then you pretty much do the computation that we did earlier. Okay, so try to think about this case. Another thing to check is that you can use the following approximations. So in particular, when delta is between 0 and 1, you can simplify these expressions and upper bounded by something like e to the minus delta square mu divided by some constant. 3 suffices. So it's a relatively clean bound to use, and in particular, you can say that the probability that z minus mu, the deviation is at least delta times mu in either direction, is upper bounded by the sum of the two things above. So it's 2 times e to the minus delta square. And let me quickly show how this bound compares to what we computed earlier. So let's talk about the case when we have a sum of independent Bernoulli random variables, which are also identical and in fact are one with probability half, 0 with probability half. We sort of saw what Markov's inequality gives us if we want to compute, let's say, the probability that z is greater than or equal to 3 n over 4. The expectation of z is n over 2, by the way. What Chebyshev's inequality gives us, and these are bounds we computed earlier. And just for comparison's sake, let's see what the Chernoff-Hoeffding bound gives us, or when z is, in this case, it is a sum of mutually independent Bernoulli random variables. So we are in a setting where we can apply Chernoff-Hoeffding bounds. So this can be written as probability that z is greater than or equal to 1 plus 1/2 times n over 2, which is the expectation of z, which is what we also call mu. So by the bound on the previous slide, also, let's say we use one of this when delta is, for us, delta is half, which is certainly between 0 and 1. So you can use one of these bounds. So we will get a bound of the form e to the minus delta square mu times 1/3, or e to the minus n 24, I guess. So in particular, the bound is much, much stronger than even what we obtained by Chebyshev's inequality. So Chebyshev's inequality gives us a probability which is going to 0, but Chernoff-Hoeffding gives us a much stronger bound than that probability. And some sense it's fair to ask, once the probability is going to 0, why do we care if it's kind of going to 0 just at a fast rate or just at a very, very fast rate? And we'll see maybe in the next lecture. In particular, this is useful when we want to not just talk about the probability of one bad event, but we want to rule out the probability of many, many bad events at the same time, which is what's called a union bound. Or okay, one way of doing that is a union bound. And Chernoff-Hoeffding bounds are strong enough for us to be able to take union bounds. And I'll show an example in the next lecture. Also, there's some problems in the homework which kind of illustrate this. But let me stop here for today.